Okay, so this last example from this chapter, we technically will not be looking at until the next day of class, but since one of my classes I still won't be there that day, I'm going to have this recorded as well. And we're going to be considering equations of exponential functions. So when we have exponents set equal to one another, and this book calls this the property of equality of exponential functions. All right, and this is what it says. It says, suppose B is let's see, and this B I'm talking about is one of our bases, is a positive number other than 1. And then b to the x 1 equals b to the x 2 if and only if x1 is equal to x2. Alright, so the idea is this, that if I have two things of the same base equal to one another, then their exponents as well must be equal. Alright, so let's consider, and pause this if you do need to write this down. This is also found on page 599 in the Red Algebra 2 textbook. So in using this property, if I have something to the effect of, actually let me do an easier one first. What if I have 5 to the 2n equals 5 to the, let's say, 7. We'll do n plus 1. Alright, the idea is if I have two things of the same base equal to each other, I can actually boil this down or reduce this to just being the exponents being equal to one another. So 2n must equal n plus 1. And now I could solve this normally, subtract n from both sides, and I'd have n equals 1. And notice if I plug 1 back into the original problem for both values of n, I would have 5 to the 2 times 1 equals 5 to the 1 plus 1, and 5 squared equals 5 squared, or 25 equals 25, being a true statement. So this is the general idea, and it does only work when I have things of the same base, but when I have two exponents or exponential functions equal to one another, if their bases are the same, then we can conclude that their exponents must also be equal. And that's the general idea. So let's consider a more interesting example. What if the bases aren't quite the same? So what if I have, for instance, 64 equals 2 to the 3n plus 1. Now 64 is technically being raised to the first power here, but I can't just say 1 must equal 3n plus 1 because the bases were not the same. However, notice 64 is actually a power of 2. So I could rewrite 64 as being 2 to the 6th power, I believe, which is still going to equal this right-hand side, so 3n plus 1. And now that I have two things of the same base equal to each other, I can in fact boil this down to being their exponents equal to one another. So 6 must have equaled 3n plus 1. And I can solve, subtract 1 from both sides. I will get 5 equals 3n, and then divide by 3, and I will get n equals 5/3. Which, if I do a check, the original problem only had one location for n, So I would have 64. Is that in fact equal to 2 to the 3 times, and instead of n I'm plugging in 5/3. Looks a little weird, but it actually works out quite nice. Plus 1 in the exponent. 64 equals 2 to the, notice the 3's here would just cancel out. So that's 5 plus 1. 5 plus 1 is 6. And 2 to the 6th is in fact equal to 64. So it does check out. So this is the more interesting case when I did not in fact start with 2 of the same base, but it turned out that this base was merely a power of the other one, which I was able to rewrite. So that's the trick that allowed me to solve this problem. So let's consider another example like this, and this will be the last example from this section. This is a little bit more unique. 6 to the 2n minus 1, actually this is even inequality, is greater than 1 over 216. So it turns out this property also will have similar effects here. Now 6 is the base on the left side, and 1/216th is the base on the right side. So I can't say anything immediate about this relationship, but I may realize that 1/216th actually is a power of 6. By the way, 6 to the 3rd power is 216. So 6 to what power would equal 1/216th? Well, I would just have to make that exponent negative, so I could think of this as being 6 to the 2n minus 1. Oh, going with an equal sign there. Should be greater than, or when is this greater than, 6 to the negative 3rd power. Alright, so I'm rewriting that as a base, or as a power of 6. And now that I have two things of the same base being related to one another, I could conclude that, well, if this is really greater than that, then it must have been their exponents that were having that effect, not in fact their bases. So I can boil this down to being 2n minus 1 must be greater than negative 3. And I can solve this like a regular equation. 2n is greater than negative 2. So n, when I divide by 2 on both sides, must have been greater than negative 1. So this is a true statement whenever n is greater than negative 1. And just we can, so n equaling negative 1 in fact is not the working case, but we can do a check with it, and we should realize that I mean, I could even try a value like 0, for instance, would work for us. But I actually want to look at this point right here. So 6 to the 2 to the negative 1 minus 1, is that going to be greater than 1 over 2/16? And that the answer should be no to this. They should actually end up being equal in this case. So that's 6 to the negative 2 minus 1 greater than 1/216, or 6 to the negative 3 greater than 1/216. And this is a false statement. It's not greater than, it's actually equal to. But I think you guys would agree that any value bigger than that, alright, like negative 2.999 even, would be greater than 1 over 216. So that's why n being greater than negative 1, alright, would actually give us the same outcome. Alright, so all values of n greater than negative 1 would make this original statement true. And once again, I want to point out this does not work for all cases. For instance, if I even change this to a 217, we would not be able to solve this problem in this current form with our current skills. And actually, it will be the next chapter, or not actually next section, where we'll learn the skill of solving equations with variables within exponents when we can't write them in terms of the same base. And we'll have a very powerful tool to do so. Alright, so please feel free to email me if you guys have any questions when trying the homework or even the classwork. I hope that you can watch or rewatch these examples, prior to doing each example for the classwork if you need further explanation. And once again, all of this content is found within the Red Algebra 2 textbook on page 596 all the way through page work be up to page 602. Alright, so I hope you have a wonderful day, and I'll talk to you later.